Hi, everyone. Thank you for coming to another series of the ISI seminar. Today, we have Oliver Liu, who's a second-year PhD student at our own Institute, University of Southern California. He's co-advised by Professor Danny Yogatama and Professor Willie Neiswanger, who's here with us in person, so that's great. Oliver's research interests usually lie in multimodal foundation models, and especially their algorithmic reasoning capabilities and applications in sciences. And today he will be sharing us about understanding the uncertainty of language models with his new framework that he's recently published. So please, without further ado, let's welcome Oliver.
Hi everyone, my name is Oliver. I published by Ollie because there are two other Oliver Lius at USC, and they have much better user handles. It's just oliu@usc.edu, so I miss a lot of emails because of that. So Ollie it is. So this is a recent work that we put on archive that talks about using large language models for decision making under uncertainty. So this is a joint work with Doqin, who I believe is in Zoom, Dani, my co-advisor, as well as Willie. Who's here. This is a little avatar that we created for our decision-making agents. So you can see that there's like different top choices over here, and there are multiple paths that they can choose. And the model is having a dilemma, which is why we call it dilemma. Okay, cool. So first, I want to talk about decision-making under uncertainty, which has been a well-studied mathematical model to guide us towards rational and optimal decision-making. Or so it's like a mathematical model for a human framework to guide us to do decisions. And it is ubiquitous in our lives, includes many applications. So for example, agriculture planning, market investing. So for example, portfolio investment is a decision-making uncertainty problem. Some others include medical treatments, for example, kidney allocation. Like for example, in COVID-19, there are respirators kind of treatments, stuff like that, allocations. And also we have some others such as scientific discovery. So I think Willie has worked on a few things like Bayesian optimization for material science discovery and things like that. And it has been extensively studied in economics, statistics, and philosophy under different names. For example, discrete choice theory, statistical decision making, things like that. Right. So the key idea is that since it's been so extensively studied, why are we still using large language models to study such a well-studied idea? Well, the first thing is large language models are powerful common sense reasoners, and a lot of the decision-making uncertainty problems, such as the ones presented before, involves a lot of common sense reasoning. So for example, if I'm to invest in agriculture, then probably it's better for me to reason about what's the temperature, what's the geography of the location, and LLMs can provide a good prior on this kind of information. And the second one is that it provides a more user-friendly interface than traditional statistical approaches. So for example, a lot of the prior works on decision-making uncertainty involves Bayesian networks or probabilistic graphical models, which are pretty involved for us to actually study and develop. And also these models are not that good at consuming, for example, natural language inputs, which are often prevalent in decision-making uncertainty scenarios. And there's a recent work from UC Berkeley that talks about large language models are reasonable out of the box forecasters. So for example, they collected a bunch of data sets from these forecasting platforms, and they show that GPT-4 are especially good at making this kind of forecasting predictions, even the data is actually not in the text. So here they're reporting brighter scores, so lower is better, and random guess is about 0.25. So it's a little bit above this kind of random guess, but still far from human. And they show that there's a system in place that it can actually make that forecasting better. But still, forecasting is somewhat of a thing that large language models can help humans that can be used. Yeah. Okay. But the core challenge that we're going to tackle in this project is that they're not really out-of-the-box decision makers. So I'm going to use decision making and with an abbreviation for decision making uncertainty here. So I'll give a concrete example. So here we have some agricultural planning data set that we're deciding between whether we're going to plant avocado or grape for the forthcoming agriculture year. And the ground truth here is avocado. Decided by the total revenue per acre. And we're going to give some context. I'm going to omit it because there's too much text. But here is some avocado product summary as context, and there's some grape product summary as context. And there's some instruction, which is basically saying that I'm a farmer in California planning what to do in the next agriculture year. I'm gonna invest all in avocado or grape, right? And the GPT-4 gives a wrong prediction. And this is its explanation. And I'm not gonna ask you to read through all of it, but why? So you can see here that they're too, the TLDR version is that they're too good of an in-context learner, meaning that they're just copy pasting the sentiment or presented in context, for example, here in avocado, and say that, okay, so this is the thing that's expressed in this summary, so I should probably just follow that. And they also have this context for grape, which is basically saying that the grape production is forecasted to be up despite the drought and heat conditions. So, okay, that sounds good. So I'm gonna just follow that and predict that we're gonna plant with grape. But agriculture planning is much more sophisticated, which we'll see in our actual data set. And so the model cannot reason with this kind of uncertainty, even if we're doing chain of thought reasoning for this kind of thing. Right?
Sorry for questions. So what are the supporting information in the text for avocado that the model is missing?
So for avocado, it's actually not missing anything. It says that avocado production has decreased due to the past year, which is actually not missing. So like it's kind of a reinforcing avocado decrease, grape forecasted to increase. So we're gonna invest in grape, but this is actually not the case in the next year.
I mean, it's not what happened.
It's not what happened.
But like, given this information, would a reasonable person choose avocado and GPT-4 did not?
Right. Actually, GPT-4, a reasonable person would also choose avocado grape, but it's actually not grape. That's actually the optimal prediction. So,
okay, so
yeah.
The complaint is that GPT-4 is not omniscient.
Right. It's omniscient.
And we're going to show us how to make it omniscient.
Well, we're going to try to, but yeah.
Okay.
There is it's kind of interesting that like this kind of simple framework can actually improve. So yeah, so they're just they're very good at in-context learning, but they actually, but as we shall see later, so this is like a systematic behavior that we observe that scope beyond decision-making uncertainty. It's just that they are too good of an inductive reasoner, so that they cannot actually reason with stochasticity presented in context. And so this is something that's been actively discussed with another recent column submission from a group at University of Pennsylvania. Okay, so we're going to talk about decision-making uncertainty with large language models. So our goal is to search for the actions that maximizes the expected utility. So I'm going to give a mathematical definition, then we're going to see a concrete example. So our goal is to maximize the expected utility subject to some state uncertainty. So this here theta is what we call the future state. So for example, like the weather in the next coming year, or market conditions, or things like that. So we actually do not know this information a priori. So we're going to prompt the language model to enumerate or elicit a bunch of states that we're going to use for this kind of decision-making tasks. So we call this task state enumeration. And the second one is this distribution thing, which is what we call state forecasting, meaning that given a context, for example, this current year agriculture report, we're going to generate a distribution of this future state with a large language model. So this is the forecasting part that we just reported that GPT-4 can be a good reasoner about. The next one is going to be utility elicitation, meaning that usually we know the price of the fruit in the current year, but we actually do not know, given, for example, the future market condition, as well as what agriculture crop to invest in, what the utility is going to be. And this is something that's very prevalent in a sense that a lot of the reward functions for this kind of decision-making process are not explicitly being defined. So we're going to try to use a large language model to do that. And finally, this is the optimization step, which is for discrete action spaces, we're going to choose the max by enumerating computing the utility functions and get the optimal utility, expected utility out of it. So all of these color-coded things, we're going to try to tackle in a very preliminary sense in DeLLMa, which is short form for decision-making large language model assistant. I want to credit Goqin to come up with this great name, although initially I want to call it DeLLMa for a lot of times, but it's pronounced as DeLLMa. Okay, cool. Okay, so just to give a concrete example. So here we have a decision-making uncertainty problem where we have a future state. Okay, it's under fire.
I think we can just plug it in.
Yeah, sounds good. Okay, Howard, back on. Okay, so the future state is that I have a house and I'm gonna decide whether I want to buy insurance or not. And the future state is that there could be possibly fire, no fire. And if I invest in insurance, I will get some reimbursement. But if I do not, I will lose my house, and but potentially I will keep the original insurance investment money, right? And so this is like a decision-making graph, meaning that we can take either of these actions, whether to do insurance and no insurance. There is a possible future state distribution, which is the forecasting part, so that if there's a 5% probability if there's going to be fire, 95% of probability if there's not going to be fire. And if this is the outcome, I will have no house, but I'll have the reimbursement. And if there's no fire, I will not keep the original $100 that invest in insurance, but I will keep the house, which is valued at $500,000. Right. And so there's also like the fire, no fire situation here. But in this case, if there's a fire and I do not have insurance, I will keep the original $100, but I will lose the house. But if it's the best case scenario, I will keep my insurance money as well as the house. So I think it's pretty obvious what you should do here. So do this usually, especially that the reimbursement. Yeah, the housing market is kind of crazy. So yeah. Yeah, that's a good point too. Not sure what's the situation with boat, but
yeah, with slightly different numbers. That situation.
I got you.
Yeah, earthquake insurance is more realistic.
Got it. Okay. All right. So I'm gonna color code everything. This is like the 4 formal procedures of DeLLMa. And so the input of DeLLMa is a prompt which is a triplet which concerns of a user goal. So for example, in the agriculture example, we're gonna maximize our next year revenue. And we have a set of actions, and in our original example, that would be invest all in avocado or invest all in grape. And we also have a context C, which is something like the current year agriculture report. And so we have the 4 steps: state evaluation, state forecasting, utility function elicitation, and expected utility maximization. So we're gonna go through each of them step by step. Okay, so the first one we're gonna talk about is state enumeration, which is essentially the procedure of, given the current context and goal, what is the probable future state that we should be concerned about, right? And so our goal is to produce a list of M states. So M is the total cardinality of the states. And so this is, yeah, just some mathematical notations here. And each state, theta is a state of K factors. So for example, you can think of this factors quoted by F1 through Fk. So I'm gonna give a concrete example. So this is the prompt. And so we have goal, maximize revenue, and our context are primarily the USDA reports that we collected. And so we're going to prompt the LLM to think about, hey, what's the important factors here that we should be concerned about? So the first one, of course, is weather. Second one is probably supply chain, because there's a lot of COVID uncertainties with respect to agriculture planning. And the third one is, for example, popularity. So this is not too much of a concern, but turns out it somewhat is as well. Okay, so sorry, the notation is a bit heavy here, but for each of the factor F, it may take L possible values, which we denote as F1 through FL. In the example here, for example, for the weather factor, it can take 3 possible values: sunny, raining, and snowy. And supply chain, something like humanity's SpaceX is gonna develop some shipping rocket, or like there's gonna be a complete supply chain lockdown, or overseas shipping has increased. So this is something that we can also be concerned about. Also popularity. So like, for example, avocado somehow becomes very hot right now, or people hate avocado, or something like people are turning middling towards avocado, right? Right, so these are the factors, and all of this we're gonna, so for now, we're trying to develop a very preliminary framework by putting everything within a large language model. But in the future, these things can definitely be improved with tool usage, retrieval augmentation, or better calibration tools. So the second way,
just what you put in, how you get it.
Yes, I do have. So this is coming out. Yeah. I told Justin that there's just too much animations in there, so sometimes it's pretty slow to go through the slides. Okay, so there is an example here. So for example, this is so actually this is not like the complete example, but I just want to give you that. For example, I put in the product summaries. I asked the model to say that I want to like maximize my revenue. What are the potential weighted factors in the upcoming agriculture year that I should be concerned about? So the model will give us something like climate conditions, supply chain disruptions, demand, as well as like the price yield for each of the respective fruit, right? And so I'm gonna come back to this example very soon. But so this part is concerned about state forecasting, which is essentially that given a set of context and a set of states, what are the probable distribution of the states that it should be with which that it should be computing the expected utility event. So let's assume that there is a ground truth state pi theta condition on C, and we're gonna try to construct a approximation of the distribution by plotting the LLM. And but this state is kind of large, right? Because we have k factors, and each k factor can presumably take on L states. So this space is exponential, and we're going to try to. So this is kind of challenging. So we're going to use a very simple strategy by decomposing them by assuming that they're conditionally independent of each other by conditioning on the context. So we're going to generate k conditional distributions, one for each of the factors at phi, and we're going to define the LLM forecasting distribution as their product distribution. So this is the entire algorithm. It's kind of notation heavy, but the key idea is that we're going to prompt the model to give a belief or likelihood score verbalized in natural language. And from those verbalized natural language belief scores, we're going to convert them into numerical values and normalize them to generate a belief distribution. So here's the idea. We're going to prompt the model. We're going to let the model generate something like the belief. For example, this is very likely maps to 6, very unlikely maps to 1. And we have this, and suppose that we're thinking about weathers. So for the weathers, we have 3 plausible outcomes. And for each, the model will say that this is somewhat likely, this is not that likely, and this is very unlikely. This is probably Seattle because it's not ever sunny. But okay, so by normalize, we just say that we're going to normalize it to so that it completes a distribution. And we're going to do that for all of the factors that we're interested in. And we're going to make a product distribution of them to get like the forecasting distribution. So of course, this part can also be improved by existing statistical learning tools and retrieval augmentation to get the more relevant context. But yeah.
So you're using off-the-shelf pre-trained LLMs for this?
GPT-4. Like, when we were doing this project, Cloud 3 was not around, and this is like a very challenging thing even for GPT-4. So that's like what we do for now. But definitely, that's one of the future directions I want to do, like by distilling this kind of decision-making capabilities to small language models and see what we can do about it. Maybe Llama 3 is a good candidate since it just came out. Yeah.
My concern in general about like predicting categories with the language model, and we see this in language models for annotation all the time, is that the logits are influenced by a ton of factors that we don't know, including like what kind of RLHF schemes are going on. Like, for example, if the logits, if let's say rainy is a lot of human preference data indicates that, like, you know, we don't like the LLM to generate the word rainy that much. That will be impacting the logits in a way that has nothing to do with forecasting. It has everything to do with like a vague notion of like toxicity or human preference data or whatever. So I'm like, it's one of my skepticisms around LLMs for annotation, and like I see that being an issue in this area as well.
For sure, I absolutely agree with that. I think LLMs are suitable for generating what are the states or that we should be concerned about, but we should ideally really delegate this part to an external tool or external statistical tools to do that. So for now, we just want to like scaffold and see LLMs can improve decision making. But yes, that's definitely one of the future directions. And also, I think there's a more nuanced scenario wherein, for example, we're concerned about the LLMs is going to generate it's going to have, for example, 80% of raining days in the next agriculture year, but this 80%, this 80 could have, for example, a logit probability of 100% or something. So this is like, so this kind of uncertainty in terms of its formalized score as well as its actual logit probability is actually could be some there could be some distinctions there that we're not like so sure about. So there's also one of the recent work that talks about can LLMs simulate pseudo-random sequences. For example, simulate result of flip coins with like bias probability. It actually can to interesting precisions. So there's like more interesting interactions going on there, I believe. Yeah, that's a great question. Cool. And so just to coming back to this example, here we actually are prompting the model to generate these kind of verbalized scores. This is like the in-context demonstration of what the output should look like, but this is actually not the the actual output where we're just letting the model to generate that on the fly. Okay. I should really just quit the slides and come back here. Okay. So the next step is going to be utility elicitation, meaning that we're going to try to approximate this function with a large language model. And I believe actually that this part would be something that should ideally be good for large language models to reason about. So the utility function, by definition, takes a state action pair from state theta and action A, and gives us a scalar value function, which is some score, or in RL we typically call it reward. Where if this is utility is more like an economic thing, right? So the key idea is that we're gonna use LLMs to rank state action pairs. So for example, is the I state action pair theta AI preferred over the other state action pair theta AJ?
Sorry, the I and J are subscripted to the tuple so that theta can change, you're saying?
Yeah. So theta I and theta J. So just
state. Wait, say that again.
Sorry. So this is kind of a abuse of limitation, but what it really means is theta I and AI, meaning that like it could be completely different.
Okay. So not a different, not a conditional distribution, but joint.
Right. It's a joint distribution. Yeah. And we're gonna collect a data set of pairwise comparisons in this form. So we're gonna elicit some preference with a large language model. And we're gonna do utility installation with a Bradley-Terry model. So we're getting back into the RLHF step, but like this is how originally Bradley-Terry model has been used. So what the Bradley-Terry model is doing is that we're gonna fit this omega like offset of preferences into the Bradley-Terry model, and it's gonna give us a vector of dimension S, where S is the total number of uniquely sampled state action pairs that we're going to care about. So, for example, if we have 100 distinct state action pairs, this is going to be R100. Okay, and I will give you like a concrete example here. So here I'm going to use 3 and 1 to index the state action pairs. Right. So here what I'm saying is that 3 is preferred over 1, and here we're saying that 1 is preferred over 5, 3 preferred over 2. Sorry, 2 preferred over 3. Wait, actually, I don't. But yeah, so this is the complete preference graph, for example, and we're gonna feed it through a Bradley-Terry model. So here, notice that we have 5 unique state action pairs. So the dimension of the Bradley-Terry model will be 5.
Wait, 6. 6 lines.
Oh, but there are 5 states. 5 state action pairs, and there are 6
state action pairs of the nodes.
Yeah, 6 comparisons. But at the end of the day, what we really care about is the utility associated with each of the state action pair. And yeah, if we just parse through the graph, you can see that 1 and 2 are maybe there's not much of a difference because they're all 3. We prefer 3 over both of them. So 3 has like the highest utility, and 4 has the lowest, and 5 is being preferred over by 1 and 2, so it has the second lowest, something like that. So we're going to do this for all of the state action pairs that we're going to sample from the forecasting distribution as well as the possible action space through a large language model for a decision-making task. So the question is, we are going to get this kind of preferences what we're going to try to get it in a more efficient manner, because if we're going to do pairwise comparisons for all of our state action samples, that's going to be super duper expensive, and we don't have the budgets to prompt GPT-4 that many times. So the goal here is that we want to get accurate utility by ranking them with as good of a ranking as possible. And we're going to try to make it with a small number of API queries. So we're going to color code this desiderative accurate utility in pink, this desiderative small number of API queries in blue. This is our entire algorithm that we're going to go through it step by step. So the input of this algorithm is, again, contains the prompt of goal, action state, action sets, and the context. We're going to talk about and we also have a proposal distribution as a result of our state enumeration and state forecasting procedures. And also we have a sample size S, which is the total number of unique state action pairs that we're going to sample. And here, this is like a little bit of for these implementation concerns, we're going to have a mini batch size B. And we're going to have a overlap proportion cube, which we're going to talk about in a little bit. So first of all, we're going to sample fixed states for each action, meaning that for this discrete action space, each of the actions is going to get the same set of state samples. So this is kind of like a variance reduction procedure, so that each of them will get like the same set of states, so that utility elicitation quality may be improved a little bit. We found in our ablation that it actually helps. And so this is our state action data set. And we're going to shuffle it. Oh, by the way, so this part is not being done by a large language model at all, because why would you sample from a probability distribution using a large language model? So this is being done by a Python program. And we're going to shuffle it, and we're going to construct from here a bunch of pairwise comparisons. And this pairwise comparisons data set is going to be called omega. And for here, what we're essentially doing is that we're going to feed the current mini batch of state action samples to the large language model M, along with the prompt P. And we're going to ask the model that, hey, could you help me rank this set of state action pairs? And the model is going to give us a rank. So for example, if we have 40 state action pairs, the model is going to give us a list of essentially permutation of this 1 through 40. And we're going to use that as our ranking. We're going to use that ranking to convert them into our pairwise comparisons.
Sorry.
Yeah.
So the LLM is going to say, given the context, which is like the text example, what individually for a particular feature, what is the distribution of the values of that feature, right?
Right.
Individually, and then so the initially independent product of those is going to be the ultimate probability of the state, right? The state is just the conjunction of the values of the features. That's the thing that you do by Python.
Right.
And the action is not relevant. That you just can staple any action onto everything.
Yeah. Right? Yes.
Okay, cool.
Yep. And so yeah, this will give us a ranking, and we're going to convert those rankings into pairwise comparisons. So for example, if state action pair 13 is preferred over all the others, we're going to do state action pair. We're going to construct omega with action pair 13 to all of the other indices, for example. So this will give us a, so if the mini batch size is B, this is going to give us OB squared number of pairwise comparisons. So this is what the, essentially the format rank part is doing. But there's a significant problem in this procedure because, for example, if there is no overlap in between our mini batches, the preference information that we're going to get for each of the mini batch is not going to propagate throughout this big computation graph. So think about this figure here. If we're doing no overlap mini batch sampling, this could be something like this. Like 3 is preferred over 1 and 2, and the 5 is preferred over 4. But there is no this kind of pairwise information comparison in between these things. So that's why we have to introduce this notion. Come on, introduce this notion of overlapped batch sampling, because otherwise, so just for the sake of, we're gonna propagate the entire preference graph together.
Is there in the theory like a minimum amount of overlap at which
there is
the utility propagation?
Yeah, there's not really a theory, but we did do like a lot of ablation studies for these kind of things. Just to give a graphical example, so these are, so we have two action states, two actions A1 and A2 here, and each of them are going to be assigned with 4 states. So they're going to be color coded. So you can see that like each state, each action get the same 4 states. And what we're doing here is that these dotted squares are actually being shared for mini batch 1 and 2. these dashed squares are being shared between batch 2 and 3. So all of this entire preference round is constructed so that we can propagate at least some information through there. And arguably the easiest one is that we're going to maximize the expected utility, which is this part. And because we're dealing with discrete action spaces, what we're doing is very simple, because we have a broadly Terry model outputs state action pairs, and we're going to select for each action what are the output of the broadly Terry model that correspond to that specific action, and we're going to take an average of those actions, right? And for these, they're going to be the expected utility marginalized over for the state, marginalized over the states, and this will give us the expected utility of choosing that action. And it's going to be very simple. We're going to enumerate over all the set of distinct actions that are going to take an argmax. So there's no fancy like gradient descent optimization going on here, just for this preliminary task. And again, this is performed analytically without large language models, because why would you need that with a large language model?
So in the last step, you did use the large language models used. You give it a state and an action, 2 states and an action, and say, given each of these states. And you also give it the context at that point?
So for this part, there's no actual
previous part.
Okay.
The P part.
So the
Preference ranking.
The preference ranking. Yes, we did give it
the lower rank the mini batch part.
Right. So this part we actually did give it the prompt.
You give it the context,
The
context, and then you say, and so it's like rain is not likely or something like that. But but given that there is rain and this happened, right? Versus given that this happened, this happened, which is preferred for choosing grapes.
Yes, exactly. And we need to, so just a small comment here, we need to shuffle the mini batch, because otherwise, so for example, like if they're just ordered perfectly, sometimes the model can get into hallucination zone by saying that, okay, we have action 1, action 2, action 3, state 1, state 2, state 3. Okay, right. So it's ordered. So I'm going to do 1, 2, 3, 4, 5, 6. So we need to like do the randomization a little bit.
Sounds like a hard lesson learned.
Oh, yeah.
So, out of curiosity, when you first motivated this, you showed sort of like the insurance payouts of your house catching on fire. And there, you directly estimated a utility for each state action pair.
Mm-hmm.
But here, you're doing something more complicated. Is this because you felt that LLMs could not directly estimate a numerical utility, and that this sort of preference estimation would be more robust, or did you try directly estimating a utility value?
So I think we're just trying to operate in a more general setting where utility function is not very intrinsically specified by a user. So I think in the agriculture example, the utility is actually very crystal clear. It's just an extra revenue. But I think we believe in a lot of cases, these kind of things are not being specified. And also, we do not really have the actual utility, the ground truth utility, where you consume the state action pair and get an output.
So do you have preference information then between 2 pairs? I mean, it's the same problem, right?
Right. So I believe with enough, like if you're just looking at the data for long enough, we can actually get the preference information. So that is actually desired.
What does that mean if you look at the data?
So for example, if we have rain, if we have like major supply chain disruptions and we plant grape, is it actually more preferred over, for example, no rain, no supply disruption, and avocado? So this is, so with enough prior knowledge, we can actually do this kind of pairwise comparisons, but it's going to be very time consuming and challenging for humans to do.
Yeah, I mean, I don't know, like to play devil's advocate, you could also have a proxy of, profits or something that would be utility. And you could also kind of, the same thing you said about state estimation, right? We don't necessarily know that the LLM knows the probability of rain or whatever. So maybe it can make up a number for, SpaceX developing rocket-based transport and it being rainy reasonably well. So it's just sort of an interesting question of why would you trust the LLM to estimate these probabilities, but not trust it to estimate utilities? Is it because you think it knows more about probabilities from historical data than it does about utility estimation?
I think that's a great point with respect to LLM's data estimated state probability, because at the end of the day, when we found that because our probability forecasting is very coarse-grained, so at the end of the day, we actually have like really diverse or somewhat uniform samples of the state distributions. And what LLM is really good at is essentially trying to be grounded with respect to those states and say whether certain state action pairs is more preferable to the other.
Yes, I mean, one last, you could do the same thing with pairwise estimation for your states, right?
Yes, exactly.
And then try to get a similar kind of thing. So yeah, I mean, it's sort of an interesting.
Yeah, it's definitely like I would definitely do think that there's a lot of parts that are moving here, so that like a lot of them can be improved. And also, just to give a quick comment, we also think that like maybe Bradley-Terry model is not the most suitable here because sometimes maybe the model could be indifferent towards certain pairs of state actions and things like that. So maybe this kind of elicitation procedure could definitely be improved. But overall, I believe that this is kind of, so I come from the operations research world where there's a lot of optimization going on. And I think that overall this fits in the regime of simulation optimization, where we want to simulate some potential outcomes. And with those potential outcomes, we're going to optimize with respect to a stochastic objective function. And we're going to try to, and there's a lot of moving piece with respect to uncertainty, with respect to preference. This is where we want to actually delegate to large language models. Because they're not really good probabilistic reasoners, but maybe with enough common sense, they can be used to rank this kind of state action pairs. So this is the overall flowchart. So graphically, so we have some goal. I'm a farmer in California, want to maximize revenue. In stock market, I'm a stock investor trying to earn. So this is like the market historical data that we have or the context of USDA reports. And we're going to first let the model to forecast the unknown states as well as the unknown state distribution, such as climate, price, supply chain disruptions, prices, regulations, product launches. So these are all computed by the large language model. We're going to use it to do utility elicitation, and then we're going to marginalize through all of the states. And we're going to take the action that maximizes the expected utility. Okay. So we have two data sets that are curated by the authors. So the first one is agriculture planning. We really like this one because it actually is a real data set that we just copy pasted all the information from the PDFs of USDA. So there's context, which are the USDA reports, and cost to produce, price, and yield. So it's a little bit of a forecasting problem as well as try to ground it in some more realistic scenarios. And also we have a goal, which is to maximize the revenue for next year. And the action is to select one product to plant. So there, because this is like incredibly data not intensive. So we only have 7 products that are actually available in the USDA reports, and as well as has the California price and yield statistic, official price and yield statistic published by the USDA. And so just to illustrate how difficult this problem is, so this is the current year price of the 7 fruits that we're concerned about. So this one is actually grapefruit, but there's no grapefruit emojis, so I used tangerine. And if we can make an educated guess of what the next year price per acre of these fruits will be, do you think it will change a lot, or would it be relatively similar?
Which years?
So this is 2022, and this is 2023.
There's a lot of rain.
Yeah.
23, 22, yeah. So.
Yes, it's like this. So grapefruit is no longer fashionable anymore, apparently. So the reason here is because in 2022, there is Storm Uri in Texas, and the grapefruit production has been extremely decreased. And so this is kind of an anomaly. And in 2023, actually, this situation has been fixed. So grapefruit is no longer that expensive anymore. But you can see it's almost like an entire permutation without preserving much of the order. So it's kind of interesting. Yeah. I actually didn't know that the price changed that much.
Food prices are notoriously
yeah.
Really
Just think that
They took away the emoji. So farmers are making these decisions themselves, right? Yes.
Yeah, I think so.
Just looking at farmers are looking at these reports and deciding every year.
Yeah.
It's probably much smaller decisions that then contribute to that.
Yeah. Also, like because you already have the fruits planted in the land, so sometimes, like let's say you're a startup that you want to like produce some new stuff. So maybe this is something you're starting your new farm. So this is something that you have to look at.
Yeah, I mean, this is sort of orthogonal to your overall work, but like you specifically talking about avocados and grapes, and like as far as I know, avocados don't yield their first year, right? So you actually have to do like a 5-year planning.
That's exactly.
Sure, grapes they get the first year. I suspect it's less time than avocados. But.
Yeah, there's definitely a lot of this kind of realistic scenarios to be desired, but yeah, I completely agree.
Yes. And so just wondering
how is it like a ground truth being collected from professional so at the end of the
Yes, so USDA publishes the price yield actually. So they publish this recommendation summary forecast as well as their price yield for each of the states in every agriculture
so
year.
basically if for example you choose so this year for example I'm growing apple and then next year I'm betting all in on
Like orange or something.
or just something if the price of orange is higher than apple, that means I made the correct decision.
Yeah, exactly. We also supposedly have strawberries, but strawberries price is like at here. Strawberries is so much more expensive compared to all of the other fruits, so we don't include them.
I see. So it's not from the farmer's perspective, but from the overall market perspective.
Market perspective, but there are so these prices that we collected are actually the spot prices that farmers are get when they're selling the fruits to, for example, resellers and things like that. So it's not like what you see in Whole Foods because they're always expensive.
I see, and I'm just wondering, would the context be comprehensive, to for example, because I think this ultimate goal of this data set is to recommend the next year what to grow
Yes.
to farmers. So is it comprehensive? Would this take for example, if I'm going to switch what I'm going to grow next year, is there going to be implicit a cost expenses on that?
Yes, there will be. So it will be. It is very expensive. It is very comprehensive, and we actually read through those reports, which are 50, 60 pages long, and see that they actually have the good enough information to guide the farmers. Because all of those are actually released by the USDA to guide agriculture planning, to see what farmers should grow in the next agriculture year.
Gotcha.
So usually they're a good standard, but I agree that, for example, this context collection part could be expanded using, for example, tool usage or retrieval augmentation with existing data sets and news resources.
Sounds good, thanks.
Yeah. And we also have finance investing. I would assume that this is much easier to explain the agricultural planning. So we have stock price histories over a 24-month window. And we have a goal of maximizing return for a 1 month trading window. And just to mimic the setup, the agricultural planning, we have one stock to invest, and we choose one stock to invest, and there are 7 in total. And we use GPT-4 preview 106 because that's what was available back then. And so to prevent context leakage, we're going to use the data that we collected from November of 2021 to the November of 2023 as historical context. And we're gonna try to see at the beginning of December what I should buy and calculate the total amount of return that I can earn at the end of December. So this is a 1 month trading window. And we choose some popular stocks like Google, Nvidia, tech stocks that we're more familiar with, but yeah. So there are several experiments that we're gonna talk about. So there are DeLLMa. So there are some DeLLMa variants. The first one is DeLLMa pairs, which are just we gather all of the pairwise comparisons, and the second one is DeLLMa top one, which are essentially saying that only the top ranked preference state action pair is going to be preferred over the other, and the model is different towards all of the lower ranked state action pairs. This is because sometimes we fear that large language models may hallucinate with respect to these orderings, and sometimes the first one is often the most significant. I want to see if the ranking is actually helpful or not, or sometimes ranking these state action pairs could be a challenging task in itself. I want to see if the model can actually extract useful signals there. And the third one is the DeLLMa naive version, which is without our sampling the fixed states for each action, and also with no mini batch. It's just a big batch by itself. And we also have some baseline methods, which is zero shot, which is directly saying that, okay, let's talk about give us a decision, right? And we also have self-consistency, which is the majority vote of zero shot prompting. This is to say that exactly related to Alex's question of whether it's a logic problem or is it an LLM belief problem. So maybe sampling could fix the problem a little bit. And also we have chain of thought. And for this chain of thought, we actually crafted a decision making an uncertain chain of thought by first saying that, can you give me some states and give these states, maybe we should do some reasoning. But this is without any of the Python code augmentation. So this is a reduced version of DeLLMa. And we have some experimental results. little bit running out of time here, but you can see that all of the warm colored ones are DeLLMa versions of it. So DeLLMa top one, DeLLMa pairs is our final algorithm that we're thinking about. So so 2 through 6 are the number of pairwise the number of actions that we're considering. So for example, 2 is something like avocado versus grape, and 3 is like apple, avocado, grape, or something like that. So you can see that DeLLMa is actually really good, especially for higher number of actions, which is to us pretty amazing. And also, it's also interesting that for all of the zero shot and chain of thought, they actually perform worse than some random guesses. So it's kind of it's pretty wild.
So why are you reporting accuracy?
So because right now we're doing just optimal action associated with the discrete action space. So here accuracy is sort of a synonym to whether the model is predicting with respect to the best action, the optimal action out there.
You get actual, like, how much money did you make?
Oh yes, we do. We also have that. It's in the appendix.
So was the best action the action that was taken?
Yes.
So best means what the.
Yeah. Yes. So yeah, I think like you're exactly right in that we can also have like an optimality gap in a sense that how much expected utility has been realized, even if we're choosing a suboptimal action. And those two plots are actually quite similar to each other to this one, so we didn't actually report it here. Right.
There's not no art, but there's got to be classical methods for this, for especially stocks. I mean, obviously everyone predicts stocks.
Yes.
So like, why did you? I mean, I just feel like we need more baselines. Why did you only stay within the universe of LLMs?
Right. So first of all, I think that I guess the baseline, the reason here is that we want to see whether LLMs are good enough decision making agents, and also I guess that
good enough
compared to themselves. Yes, exactly. And also I think that like stocks is the most available assets that we can have, right? Like decision-making tasks that we can have for now. But for this kind of algorithm planning, we actually do not have so much information. So yeah. But I think you're definitely right that we need to have more baselines. And now that we have more capable models like Claude 3, we should also do that as well. So
yeah, and also for the stocks, the goal is to maximize the profit.
The return. Return.
So you need to buy at a price and sell at a certain price, right? So
yes. So we're just doing like a very fixed trading window, like buying on the first day of December and selling at the last day of December. So it's like a let's say where a trader that do this kind of automated trading. We're not going to concern about like this kind of open price, close price, or any of the intraday intricacies. So baseline observations performance is kind of good, and also I guess like a key takeaway that this is actually the thing that we're more interested in is like GPT-4 cannot reason with future scenarios without these kind of state samples, meaning that if you just give it a distribution or whatever the potential future is going to be, it cannot say that, okay, let's first think about sunny and like no supply chain disruption, think about it, and then think about another scenarios, and then do this kind of grounded utility elicitation without this kind of external Python program augmentation. So I think this is kind of a thing that people has been also recently discussed about, like they cannot do this kind of stochastic reasoning, and they cannot do this kind of planning, which is why tree of thought has been developed. So we roughly view our method as a probabilistic stochastic extension of tree of thought, where tree of thought you can enumerate all of the possible states because you know how many there are out there. But for us, we actually do not know, and we need to develop a probabilistic version of it. And also, one thing that's probably not so clear in a graph is that the ranking performance is inconsistent across the domains, meaning that for DeLLMa pairs, it's actually really good for agriculture planning, but for finance, top one is actually better, meaning that for agriculture planning, maybe you can actually get some meaningful utility elicitations from the rankings, but for finance, because this task is very challenging and there are a lot of noise in there, sometimes you can just get the best scenarios and you do not have to you cannot always distinguish like the subsequently ranked pairs. And we also did some ablation studies to ablate the overlap percentage with it across each mini batch, and we also do this kind of sample size ablation study, and you can see that larger overlap percentage and larger samples from states leads to better utility elicitation. But large overlap percentage meaning that you will have more mini batch, meaning more API queries, and large sample size means that you need to do more API queries as well. So we have some cost analysis here. So for zero shot, your word count is, for example, that's just shy of 700, but for more sophisticated approaches like large sample size and large overlap, you will have like many more times of API queries. So yeah, so there's a performance cost trade-off right there. Just quickly try to sum up. So you can actually convert your DeLLMa outputs with this kind of probabilistic diagrams saying that this is a future scenario and you have a utility. So this kind of visualization tools can actually help you to see and audit what went awry when you're developing this kind of framework. So I guess this is like a really nice byproduct compared to, for example, zero-shot prompting, where you cannot know like which part does it go wrong, but for here you can actually check it out a little bit more. So there are definitely a lot of future works. We kind of did everything in a quick speed. So we definitely want to investigate the behaviors of each module, especially with respect to why do we want to use LLMs as a forecaster, and we actually want to use calibrated forecasting tools for this. And also we want to do improve the efficiency for utility elicitation by either using external tools or see how can we improve the rankings of LLM or using ranking models other than validatory. And we also want to expand data sets and navigation scenarios. So there's something like airport scheduling, meaning that you don't want to make a lot of delays. You want to like allocate the airports, the flights to different terminals and gates so that to avoid collision. And you also want to do a news recommendation. And we also want to do medical decision making, which is something that I'm most excited about. And also the ultimate goal that we want to do is that we don't want to always pay OpenAI or Anthropic money. So maybe we can distill that capability to a smaller language model. Yeah. So I also want to give a quick shout out to my amazing co-authors, DeLLMa, Danny, and Willie. I guess like take away from this picture is that if you become a professor, you can do rectangle images for students. Square images. Okay, so DeLLMa has his amazing cats in there, so I want to give a shout out to my dog. So yeah, that's my presentation.
Yeah, we have time for questions, so yeah.
Yeah, so quick question, and like, I know this is very open-ended, but did you do any application on how robust this is to like hidden information? Like, let's say like some company, like they want to do some damage control and they don't disclose like something in their report. And for example, in the case of USDA report, what happens if you like intentionally hide some part of the report as like sort of not available information? But as I said, I know it's open-ended, but did you do any evaluation study, or if not, where do you expect it to affect most? Like, for example, when it comes with the conditions to give values to any sort of information on that?
Right, I think that's a really great question. So we did do some robustness analysis, but not with respect to, for example, adversarial information, because that's kind of hard to procure. So one of the studies that we did is to incorporate all of the additional context. For example, if we're only selecting NVIDIA and Google, and we incorporate all of the context for Facebook, GME, and all the other companies, how would the model do? And the model actually performance does not change at all. So the model is really good at extracting the relevant information out of the context. But that doesn't really directly address your question, but I do think that we could investigate some more synthetic control scenarios to investigate the performance of the model. So I know that we're actually experimenting on a data set published by UC Berkeley on behavior psychologies, meaning that there are agents that are humans that are faced with decision-making tasks, and they're choosing to make a decision. And we can actually simulate that process for large language models and see how the models will perform when we apply these kind of different settings.
This work is really cool. Two comments. One, I would definitely not do news recommendation as an application. I think there's many other applications in news, some that we've talked about earlier that this could be a better fit for. And just the recommendation problem, I feel like, is a is just not one that makes sense to me.
Okay.
But my other question is like, I think you made a point about these language models doing state space recognition well and like kind of coming up with possibilities. And that makes a lot of sense to me. I mean, in some of my own work, I found that when I'm trying to use language models to do state spaces, often like they don't imagine the same state space that the humans did, and they have a less creative state space as well. And I feel like so we explore that in the source work and stuff, source plans. I imagine that like prediction tasks, especially in these areas, like there's a lot of ground truth around state spaces and stuff like that. And I wonder if you've done specific programming inside the model to like how well does it imagine the state spaces that human forecasters typically think about, or are you just looking at the end results?
Right. So I did look at, for example, some of the result because I know that I'm growing in California and in 2023 there's so much rain, but the model doesn't actually forecast there to be a lot of rain, which is actually true.
But it identified rain category as an important category.
Yes. So it identified weather as an important category, but it doesn't really forecast rain within the weather category to be with a high probability. So it's not well calibrated in that certain respect.
I see, but even it's just like got weather as a category to look at is, I think I would consider that a win. I mean, I just wonder if there's like forecasting dimensions that it consistently chooses not to look at.
Right. So I think that's a limitation in our current work in a sense that our problems usually there are some things that are very obviously important for us to look at, supply chain because of COVID and also weather because of agricultural planning. So we don't actually see a major shift between our expectation and its prediction. I think we also did like some, and also for example, for stocks, it actually proposed a list of things that I wasn't really expecting. I was thinking like market conditions, inflations, or macroeconomics, but they were thinking of like regulatory changes with respect to AI or privacy, for example. And that's actually a really good point for this kind of large-scale technological companies. So, so we do not spot major problems there, but I think it's also because our problems are pretty general. So the model will give a good list of states to look at.
I'm just looking at this right now. I figured that so finance is hard because it's very adversarial, and it's like a constant source of strife. And of course, there's great NLP background in trying to predict the stock.
Yeah.
And nobody says anything. Of course. For USDA, though, right? Like the government is actually interested in providing this information to farmers, etc. And there are these like projections of like what food prices are going to be.
Yeah.
I just noticed that apparently they changed their methods in 2023. But I don't know if have you looked at the way the USDA is doing it and how that compares. I wouldn't be surprised if it was like pretty basic and then like this could be a nice advantage over that. But if it's sophisticated, you might want to delve in.
Yeah, I think so. What I did is to look through all of the USDA reports with respect to fruits, and I think their statistical methodologies are actually just like a simple time series or this kind of forecasting that I think like we could easily augment if we have like the data source that they have.
So that's the thing, right? So the features they're putting in are probably relatively high quality. Like they could use like weather forecasting models, right?
Right. Yeah.
And you don't, but you could, right? Like you have kind of a two LLM stage approach, right?
Yeah, definitely.
So I wonder if like that would, using the latter part of your algorithm, but like feed it with like a richer context rather than just having like an LLM given like it's going to be rainy and then like having that lead to the distribution.
Right.
Probably.
That's exactly what we're planning to do because we just want to see like how if we can delegate the entire decision making process to LLMs as a valid as a baseline, and we want to iterate and develop more sophisticated tools to make, especially the forecasting part, to be more calibrated. And the recent work of Jacob Steinhardt's group has shown that you can actually use retrieval augmentation and other tool usage to improve that procedure.
I was curious, was one of your baselines one shot kind of setup where you have a DeLLMa process that was laid out for one example, and then you use that for let's say you use it for like the agricultural one and then try to use like provide one of those for like the finance example. It's out of domain, but at least the format is all there. So it can, the model knows exactly to follow those steps, but not necessarily have to do the entire like complex process and see.
I think that's a great point. I think like the core challenge here is that first, it's ours is a multi-prompt process where we actually just want to use the Python code to generate the state samples, but this state samples is actually not part of the thing that's being fed as context for the previous part. So that part is a little bit hard to simulate. I actually did like do a little bit of investigation of that in the form of playing multi-arm bandit with the model. I think that can you do like epsilon exploration, it can, but to a very limited capacity. So, but to answer your question, I didn't do like one shot because of these prompting limitations, but also I believe that it's very challenging for the model to sample these kind of states on the fly towards a better decision. And also this kind of context is really, really long. So yeah.
I was wondering if you had any human evaluation of the rankings that were done by the LLMs. Like, did you generally agree with them, or
so
reliable?
Not to a very comprehensive degree, because each mini batch is like a couple thousands of rankings, but I did read through many of the top line rankings, and they all seem reasonable. So, for example, for avocado and grapes, they're usually preferred when it's very sunny and not major supply chain disruptions, and like the price maybe does not change. So this is actually like a very reasonable preference that we can get. And also because I didn't read through all of the state action pair rankings, we did to experiment with the top line approach, and it seems reasonable for the finance scenario.
Just want, do you think this is kind of self-refinement process of LLM reasoning?
Yes, I think so. But also I think like what I'm thinking about is that, is it reasonable to expect large language models to do planning or just kind of stochastic reasoning by purely training on autoregressive models, autoregressive objectives alone? And I think the answer is pretty open-ended, but I'm a little bit pessimistic about it. So I guess like what I'm really excited about from this work is that LLMs are really good situational reasoners. So for example, if we provide a counterfactual scenario of sunny, whatever, yada, 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 the model can do some pretty good reasoning about it, but they cannot think about this kind of what if scenarios on the fly by itself, at least for now.
Yeah.
So yeah.
The next question is like, how do you comment out? There are research papers showing like LLM, if you let it do this self-refinement, it might intensify the bias like by itself. But then this bias may be like not like something like a stereotypes, but just some like maybe it would reinforce the self-belief and to make it like
yes, I think that's a great question. We didn't really do that. We did investigate why does the model, for example, perform so badly on stocks. And I think like again, the question is that it's so good as an in-context reasoner. For example, so what we give is a time series data set for stocks, right? And if you just get what's the winner of the 25 months window of the stock and compute it against the winner of the past 2 year history, they actually have 100% agreement rate. So, or 98%. So what the model is essentially doing is that, okay, given the time series history, we're going to compute the 2 year, the maximum, the optimal 2 year return. So it does that in the context, and we're going to select that as the optimal. So it's not really doing any sort of probabilistic reasoning, but it's doing like some in-context arithmetic to get the optimal stock. So, which is kind of an interesting thing that they do arithmetic in such a nice way. But so there's definitely like inductive bias, maybe because of too much instruction tuning or something right there. But we didn't actually do this kind of refinement process by itself. Cool.
Awesome. I think we're at time for overtime. So thank you so much, everyone, for coming here. Let's give another round of applause. Announcement next week, we also have another seminar. We have Matthew Phillison coming to talk about how to steal ChatGPT's embedding size and other low-ranked logic tricks. So I think that would be also another very interesting talk that will follow Oliver's talk today. So thank you, everyone. We'll see you next week.